Welcome back to our wonderful discussion about the integral test. As a reminder, what we were talking about last time is the integral test is used when we are treating our series like a function. We need a couple of things, right? First, we needed it to be decreasing, we needed positive values, and we are going to be looking at the sequence. So essentially, we're not looking at the sum, we're looking at the terms themselves before we add them together. And this is what we're checking for, right? And once we have those qualities met, if the improper integral converges, then so does our series. If it diverges, again, our series also diverges. We were in the middle of this example last time, right? Where we were looking at this series. I rewrote it to help me essentially check for positives because I'm not necessarily a fan of those negative values. With a little bit of play on numbers, we did confirm that it in fact is positive. For checking it was decreasing, we have a couple of tactics. We could use the derivative. We could list out a couple of terms and see if they're getting smaller. What we did at the last part of class was we did check out the function, but there was a difference between the function and the sequence, right? Because not the sum, we're looking at just the terms of each of these series. Whereas the domain, where our domain was 1, 2, 3, 4, positive integers, right? So our sequence looks something like this. And in fact, we do have decreasing, right? And so in comparing the function and the sequence of this series, the function looks something like this. It was decreasing for at least the tail of the graph. So there is our function in blue. And then for our sequence, we had these dots. This one right here, n equal to 1, n equal to 2, n equal to 3, so on and so forth. So in fact, we do notice, boom, it is decreasing. Done. Right? So that was step 1. Check the conditions first. Now that we've met both of those conditions, we can jump to step 2. Step 2 is to apply the integral test, right? So step 2 is your integral test if your conditions are met. Just want to stress that this doesn't always work. Be sure you're checking. Right? So there's our step 2. Let's jump in. So what I'm going to do is I am going to rewrite this series as an integral. So the integral from 1 to infinity, I got those values from right here and right here. Line them up. You can change your n's to x's if you'd like. I personally will sometimes just leave them as n's and just integrate with respect to n, but it's entirely up to you, right? So I'm going to take the limit as t goes to infinity from 1 to t to set up my improper integral. The next tactic that I'm also going to do is I am going to kind of look at this. What is the integration method that's needed, right? And what I happen to notice, let me write it up here, is that this integral, I have an inner and outer function right here. I also have what looks like a derivative, original function, and the derivative right here, right? So I notice that I have an f prime, an outer function, and an f, right? That tells me use substitution. So I am going to let my u be my inner function, which is negative n squared. I need to find a expression for dn because everything has to be switched from n's to u's. We can't have any n's left over or else this method does not apply. So the derivative of u with respect to n, negative 2n with respect to n. I'm going to solve for dn, so I'm going to divide both sides by my negative dn, so I get dn is equal to du over negative 2n. And now I'm going to substitute everything in. Right? I found out that my u is right here in the exponent spot. My dn, what was my dn? Du over negative 2n. And then canceling out n's. That's what I hope for. I hope that they all go away. All right, so now I have the limit as t goes to infinity. 1 to t. Let me zoom in just a little bit. E to the u du. I do have this like -2 or -1/2 left over. I'm just going to kind of squeeze it in the beginning. Probably could have done that first. I was in a flow though. Just look out for those constants. Don't forget them, right? So, thankfully, this integral, really, really nice, right? What's the integral of e to the u? Well, just e to the u, right? And so I'm going to evaluate e to the u from 1 to t. But remembering these are n values. So this was our first n value. This was our second n value. We need to be careful. We need to plug n back in, right? So what I'm going to do, I've got my u back over here. So -1/2 limit as t goes to infinity, e to the u. Rewrite it as e to the negative n squared, evaluated from 1 to t. So I get -1/2 limit as t goes to infinity. Let me plug these values in. I got e to the negative t squared minus e to the negative 1 squared. Let's look at these limits. Let's check out what these values are equal to. This ends up just equaling -1. So I get -1/2 limit as t goes to infinity. E to the negative t squared. You know me, again, I'm a fan of getting rid of those negative exponents. I'm going to rewrite this as e to the t squared. This e to the -1, I'm going to rewrite as 1 over e. Now what this enables us to do, right, is to essentially spotlight this limit. If this is growing to infinity, then this whole thing is going to 0. So what we have is -1/2 minus 1 over e. Oh, my apologies, times 1 over e. I knew it looked wrong for a split second there. It 1 over 2e. You know what really helps when you do stuff like I just did? Being extra with your parentheses. So if you want to include that, you can. Just making sure we're multiplying, not subtracting. So what we have found is in our tiny little corner of space left over, maybe I'll bring it over here instead, by the integral test, our series converges.